So, now we will learn some terms, because we are going to use these terms frequently throughout this class. So, first among these are phase velocities and group velocities. So, when one electromagnetic wave is propagating through free space or through one medium, or it can also propagate through any wave guiding structures. So, we are associated with two different types of velocities. The first one we call phase velocity. It represents the velocity at which the phase of the signal propagates, and it is a function of omega and beta, we will see. And another one is the group velocity. So, it sometimes we simply call it the signal velocity. So, if any given envelope is there, it represents the velocity of that envelope through the medium or through the wave guiding structure. So, let us see the first phase velocity. So, as I said, phase velocity of a wave is the rate at which the phase of the wave propagates. It can be given by omega by beta. So, where beta, this is equal to square root of k square by k c square. So, k c, it represents the cutoff wave number. So, for some wave guiding structure, we will see that it has some finite k c value, and for some other wave guiding structure, it does not have any k c value, k c equal to 0. So, beta approximately this is equal to 2 pi by lambda g, where lambda g, it represents the guided wavelength. So, that means in free space the wavelength is lambda naught. At 60 gigahertz, let us say, in free space the wavelength is 5 millimeter, but when the signal it propagates through any medium or through any wave guiding structure, its wavelength changes. So, if it propagates through any dielectric medium of dielectric constant epsilon r, then approximately lambda g, this is equal to lambda naught by square root of epsilon r. So, that means it becomes a function of the dielectric constant. And not only that, if I plot beta versus frequency, so beta is twice pi by lambda g. So, as I increase frequency, then lambda g it decreases. So, then beta it should varies with frequency linearly. So, if beta does not have any linear variation, so that means the phase velocity it will be different at different frequencies. Next one is the group velocity. So, the group velocity of a wave is the velocity with which the overall shape of the waves or waves amplitude, or we can call the envelope of the wave, it propagates, and it can be thought of as the signal velocity of the waveform, but if there is no loss only in that case, and Vg, this is del del beta of omega. So, group velocity again it should be constant and with frequency. So, we can define one term, we call it group delay. So, it can be defined for any given channel, or it can be defined for any two port network. So, let us say we have a two port network, we are transmitting any signal from port 1 to port 2. So, my receiver site is placed at port 2, then I am measuring the time delay taken by different frequency component to reach my port 2. So, if I plot this time delay versus frequency, ideally it should be constant. This is the desired thing, but practically for any channel or for any component, if I plot group delay versus frequency, it becomes actually a variable quantity, it varies. Then we face problem due to the group delay variation with frequency. What is that problem? That if I send a pulse it will have many frequency components. Now, these different frequency components will travel with different velocities, and it will take different times to reach my port 2. So, then at the receiving side, if I plot the pulse again, the shape will change. So, this effect is called dispersion, and for wideband system it is a problem. So, we can avoid dispersion by avoiding group delay variation, but for any given components we can't actually avoid this group delay variation. So, what we can do? We can minimize the group delay variation by choosing a proper designing architecture, or if this variation is too much, in that case we have to use some equalization technique which will minimize this group delay variation and minimize the dispersion effect as a whole. Now, if I measure how to measure this group delay, this is related to the angle of transmission. So, you know scattering parameters. So, the angle of transmission, that means S21, if I plot the variation of this angle with respect to omega, that will give you the group delay. So, mathematically group delay tau d, this is equal to minus del omega of angle of S21. So, by using any vector network analyzer or by any means, if we can measure the total angle from port 1 to port 2, so then we can easily calculate the group delay value. So, this is a typical group delay plot versus frequency for a passive components. So, usually for passive components we face a concave type group delay profile. So, at midband frequency the group delay is minimum, and at band edge left hand side and right hand side group delay is maximum. So, all the components it has a finite bandwidth, it can't operate over all the millimeter wave frequency or all over the electromagnetic spectrum. So, it will be higher at the left and right band edge of any given two port network. Then the second term, slow and fast wave. So, how we define slow wave? If Vp, the phase velocity, is less than c, that means the speed of light in free space, we call it slow wave. So, at fixed frequency, that means for slow wave lambda g should be smaller than lambda naught. So, Vp, then only Vp decreases and beta increases. So, we represent actually another important quantity beta by k naught. So, k naught, this is 2 pi by lambda naught in free space, and beta, this is 2 pi by lambda g for any given medium or any wave guiding structure. So, then if we plot beta by k naught, it should be actually it should not vary with frequency. So, if any wave guiding structure it supports slow wave, then usually it is non-radiating mode. So, it will guide that transmission mode through the structure and it radiates only at discontinuities. So, whenever we are going to design any wave guiding structure like microstrip line or CPW line, what we will expect? We expect that there should be some slow wave inside, so that there won't be any radiation from the structure. So, we have to keep this thing in mind also when we are going to design any components at millimeter wave frequencies as well as at microwave and RF frequencies. So, just opposite to this is the fast wave, where the phase velocity is more than that of light in free space. The disadvantage of fast wave is that it radiates continuously along its length if it is a semi open structure. So, we will see later that rectangular waveguide it supports fast wave, but since rectangular waveguide it is a closed structure, it does not radiate along its length. But if we have some semi open structure like microstrip line, it will radiate continuously along its length. So, we can't use it as a wave guiding structure then, but another application it has, that we can design antenna. Actually, there is a category of antenna which utilizes this continuous radiation along its length. We call it the leaky wave antenna, and for this leaky wave antenna, the beam direction, it is a function of beta or frequency. So, if I change frequency, then beam direction will change. So, continuous scanning is possible by frequency sweep, and in that case the attenuation constant alpha of that wave, it will determine the beam width of the signal. So, we can control the beam width of such antennas as well as the propagation direction or beam angle of the antenna. So, in this case, so lambda g should be higher, since Vp is higher and beta is lower than k naught. Another important term is skin depth. So, this term actually explain why at millimeter wave frequencies we can't use metal for wave propagation. So, how we define skin depth? This is the depth below the surface of any given conductor at which the current density has fallen to 1 by E times of Js, where Js is the surface current density value. So, now look at this top right picture. So, we are sending some electromagnetic signal through some metallic wire. Now, we are plotting the current density over the cross section of this wire. So, as you can see, this current density is highest on the surface of the wire, and if we go inside, further inside, the current density decreases. It decreases exponentially, given by this relationship J equal to Js into e to the power minus d by delta. So, if we, so what is this delta? This is the skin depth. It is given by square root of twice rho divided by omega mu r into mu naught. Rho is the resistivity of this material. So, this is approximate relationship and it holds good for metal or lower resistivity. You can replace rho by sigma, then it will be twice by omega sigma mu or mu naught. So, if I look at this expression, one important thing we observe that it is a function of omega. If I increase frequency, skin depth will decrease. So, that means at millimeter wave frequencies, this current will be mostly surface current component. It will flow through a very thin layer of metal just situated on the surface of this wire. So, since it is utilizing a very thin layer, surface resistance will be very high at millimeter wave frequencies. The surface resistance is so high, the metal, it will be very lossy. In fact, at optical wavelength, the frequency is so high, we can't use any metal at all. That is why we use in optical fiber always the dielectric material. Now, let us calculate the skin depth value for at some given at some frequencies, let us say for copper. So, if I calculate skin depth at 50 hertz for copper, it is 8.5 millimeter, and at 10 kilohertz it decreases to 660 micrometer. At 10 gigahertz it is 0.66 micrometer. If I further increase the frequency to 100 gigahertz, it is just 0.21 micrometer. So, inside the metal we do not have any current component. In other way, we can say that the metal thickness we need at millimeter wave frequencies is very small. The thumb rule is that you just take the thickness 5 times than the skin depth value. So, for example, at 100 gigahertz, if I take a metal thickness of 1 micrometer, so it is sufficient to attenuate or to support your current density. We do not have anything beyond 1 micrometer inside the wire. So, this is the general expression for skin depth, but for metal we use this simplified one. Next, boundary conditions. So, let us first consider a dielectric boundary. The first medium, it has a dielectric constant of epsilon r1, and the second medium, it has a dielectric constant of epsilon r2, and n cap, it represents the surface vector on the interface. Then from the boundary conditions, we know if we assume that no charge or surface current density is there on the interface, then the normal component of displacement vector is continuous across the boundary, and the normal component of B is continuous across the boundary. So, that means whatever we have d1 inside epsilon r2. So, if I take the perpendicular component, it is equal to d2 whatever we have in epsilon r2, it is equal to d1 in epsilon r1 if I consider just the normal component. So, similarly, it can be shown that the tangential component of electric field, it is continuous across the boundary. So, the tangential component ET1, that is equal to ET2. So, just inside medium 1 and just inside medium 2, this parallel electric field component, they are equal. Similarly, for the magnetic field H1 and H2 tangential component, they are continuous. Now, if we have a dielectric metal boundary, so second example, let us consider a PEC. So, how we define perfectly electrical conductor? So, for that sigma is infinite. So, if sigma is infinite, then we don't have any charge inside this PEC. So, in that case, all the charge, it will appear only on the metal surface or PEC surface. So, then the normal component of D, it is discontinuous by the charge density rho s. Normal component of B is 0, normal, and the tangential component of electric field is 0. So, this is one important observation for PEC, or sometimes we call it electric wall, tangential electric field component is 0. So, if there is any electric field on PEC, it might be then perpendicular, and the tangential component of H is discontinuous by the surface current density Js. Similarly, we may have magnetic wall interface. So, sometimes we call it open circuit condition. So, for magnetic wall interface, we have tangential magnetic field 0, and the relationships are given here. Normal component of D is 0, normal component of B is 0, and tangential component of electric field, it is discontinuous by an imaginary magnetic surface current density, and the tangential component of H is also 0. So, two important observation from this last two, electric wall and magnetic wall interface. For the electric wall, then we have only the normal component of electric field or tangential electric field component 0, and for the magnetic wall we have tangential magnetic field 0. So, we have only the normal component of magnetic field. So, this first one, electric wall, sometimes we call the short circuit condition, and the second one, magnetic wall, sometimes we call the open circuit condition. So, now with these terms, so let us see what are the different challenges we face at millimeter wave frequencies, and then we learn how to overcome them. So, whenever we are going to design any millimeter wave systems or any millimeter wave component, we have to deal with these challenges. So, let us start with this first one, simulation. how we design any components, we use different type of EM solver, we call it electromagnetic solver. So, what it does, it basically solves Maxwell's equation over the structure. So, we have to first define the physical structure, and then the solver automatically it discretized that physical structure and solve Maxwell's equations. And now, so that discretization number, it depends on the wavelength, and if I increase the size with respect to wavelength, so in that case we have to use more number of cells we call. So, that means the overall computational volume it will increase. So, for example, if we simulate any structure at very low frequency and the same one at very high frequency, let us say 60 gigahertz and above, so it will consume more computational resources. So, if you simulate let us say any component like a filter at 6 gigahertz, it can take let us say 10 to 15 minutes in a 3 gigahertz processor with 8 GB RAM. But if I want to design a filter for 60 gigahertz application in the same computer, it can take a few hours. So, next is design challenge. We will see later there are different sources of losses, and this loss is much higher at millimeter wave frequencies. So, how to minimize this loss when we go for any millimeter wave system design, that is really a challenge. And the second point is a single mode operation. So, for any given waveguiding structure, we prefer that there will be only one type of mode present in that structure, and there is no excitation of any higher order modes. Otherwise, these higher order modes they will increase the loss of the system and also dispersion. So, we have to avoid these higher order modes. Then next is physical realization. So, we have to choose or we have to use some materials which will give you lower loss at millimeter wave frequencies, and we also have to face the fabrication challenges, because we will see that many of the millimeter wave as well as microwave components are based on transmission line theory, and in transmission line following this transmission line theory, then this component's length will be given in terms of wavelength. So, for example, you can consider a radiating patch antenna whose length should be lambda g by 2 at the radiating frequency. Now, let us say you are designing at 60 gigahertz, free space wavelength is 5 millimeter, and in your substrate it will be 5 by root epsilon r. So, already the antenna dimension is very small. Now, due to the fabrication tolerance, if it changes by even a fraction of millimeter, so obviously now the operating frequency will change. So, you are designing some antenna for 60 gigahertz application, but due to fabrication tolerance it can operate let us say at 55 gigahertz or at 65 gigahertz, which is not desired. At microwave frequencies, since the antenna length is quite big, so we do not face usually this type of problem. So, fabrication tolerance, that is another major important issue at millimeter wave frequency range. So, next is system integration and packaging. So, finally, we have to package these millimeter wave components to protect it from different severe weather conditions. So, then what type of materials we should use for packaging, and how to package these millimeter wave components without changing their characteristics. So, it again another problem. So, we have to take into account all these issues when we are going for any design, and whenever we are going for integration for any system, then in that system as we have seen in the first picture, that we do not have only the millimeter wave components, we have also the RF and low frequency components. So, in the same module, how to integrate the millimeter wave system with the RF and low frequency system, that is another challenge, and we have to consider all these effects. So, next is testing. Once I design my component, obviously I would like to test the components, it is working at all or not, or it is giving the desired performance or not. So, we need some instruments, and at millimeter wave frequencies the instruments are very expensive. How expensive? Let us say if we want to buy one vector network analyzer, which let us say will support till 110 gigahertz, it can cost 2 crores. So, testing, that is another important factor, and it is very expensive. Only a few labs in our country has this millimeter wave facilities. Next, circuit realization. So, as we discussed that at millimeter wave frequencies the circuit size is already very small. So, fabrication is a problem, loss is a problem. So, if the circuit size becomes small, in that case its power handling capability will decrease. So, if possible, choose a proper architecture for a receiver. So, not only for receiver, for any given systems there are different architectures possible. So, for example, let us say we are going to design a receiver. So, it can be homodyne receiver, it can be super heterodyne receiver, or it can be a 6-port receiver. So, for a 6-port receiver we have many passive components part inside the receiver. For a super heterodyne receiver we have too many components, too many active components, too many filters. So, if we really want to use it for handheld device, it becomes a problem. So, for handheld device, that is why homodyne receiver is preferred or 0 IF receiver is preferred. So, then depending on applications we have to choose a proper architecture, not only for receiver, for any other millimeter wave systems. So, some systems use many VCOs. So, we have to minimize the millimeter wave components to minimize the cost of the circuit. So, if possible just use a single VCO for your whole millimeter wave system. So, again losses due to minimization of interconnects. So, interconnects, why do we need? In the system, millimeter wave system, we will be having many components obviously, starting from antenna, we have amplifier, we have mixer, we have other passive components like coupler, filter. Now, we have to use some interconnects to connect them. So, it can be any wave guiding structure, or it can be simple wire bonding or flip chip attachment, but whenever we are going to use them, we have to keep in mind that already my wavelength is very small. So, for a guiding structure, let us say if its physical length is L, so in that case total phase shift from that wave guiding structure theta, it is given by beta into L. So, beta it is a function of frequency. So, if I increase frequency for a given length L, so this theta it will increase. So, then this at millimeter wave frequencies the wavelength already is so small that if the interconnects, even if its length is 1 millimeter, it can provide substantial phase shift value. So, we have to take into account this phase shift as well as loss, signal loss when it is going through that interconnects. So, we have many more challenges. We will take a short break again and then we will continue. Thank you.